Hi friends, welcome to this first video on Green's theorem in a plane. There are going to be three important theorems when it is going to be vector integration of concern. The first one Green's, the second one Stokes, and the third one is the Gauss divergence theorem. In this video, we will see what is meant by Green's theorem, what is going to be the formula, and how we can apply it to a problem of concern. We'll move on to the main basic concept. Green's theorem. What does a Green's theorem do? It provides a relationship between a line integral and a double integral. Line integration has only one single integral, whereas a double integral has two integration, one with respect to the variable x and the other one with respect to the variable y, or two different variables that are involved in the problem. So now let us define the Green's theorem for a plane. Let us take a C to be a simple closed curve that is going to enclose a region R in the xy plane. And let P and Q be 2 points P of x comma y and Q of x comma y, and let them be having their first order partial derivatives which are going to be continuous in the region R defined. Then the theorem says integral over the closed curve C P dx plus Q dy equal to double integral over the region R dou Q by dou x, the partial derivative of Q with respect to x, minus dou P by dou y with respect to dx dy. And we have to be cautious enough to say that C is described in the anti-clockwise direction. So what we first need to take care is C is going to be what kind of curve? Simple closed curve. Simple meaning there are going to be no overlapping over here. So you have a simple closed curve over here of this sort. So C is going to be a simple closed curve. So when the curve is going to be closed, what happens? Now it encloses a region called as R. So this is going to be my region that is going to be enclosed, which is within the circle, or sorry, within the closed curve called as OC. So this becomes my region which is being enclosed over here. And in this region, what we are going to do is we are going to pick 2 points P and Q, which are going to be continuous and they have the partial derivatives defined. And now for this case, what they say is P dx plus Q dy equal to dou Q by dou x minus dou P by dou y in double integral. And how do you measure your C? In the anti-clockwise direction. That is, you go measuring your C in this way. This is your anti-clockwise. How do your clock measure? It measures in this way. So what we want is going to be anti-clockwise. So you measure it in the opposite way around. So this is going to be the orientation of your circle or the closed curve C. Okay, now let us apply it to a problem and see how does this work. Now verify Green's theorem in a plane with respect to integral over C x square minus y square dx plus 2xy dy, where C is the boundary of the rectangle in the xy plane bounded by the lines x equal to 0, x equal to a, y equal to 0 and y equal to b. So primarily what we have is the closed curve C. And how is the C defined? C is going to be a rectangle in my xy plane. So first thing is try visualizing the data, then it will become very easy for us to then evaluate the results over here. So we have the boundary to be defined. So let me have my axis of reference, my axis y and my axis x. So we have my x and the y axis over here. Now let me plot the four boundaries over here. X equal to 0, x equal to a, y equal to 0 and y equal to b. The y-axis is referred by the name x equal to 0. So if I draw the first line x equal to 0, how do I draw? I draw it in this way. So let me measure and have it in this way. This is going to be my line called as x equal to 0. Next comes my y equal to 0. What is this y equal to 0? This is my x-axis. So I have my y equal to 0 also to be got. So now next comes my x equal to a. How is x equal to a? A line parallel to your y-axis. So it is drawn in a similar pattern of your y direction. So this is going to be my quantity called as x equal to a, suppose. So this is going to be my line, say x equal to a. So I have got the third line also, and last one remaining is y equal to b. A and b are different, so don't make it into a square. Let us make it into something that resembles a rectangle in nature. So instead of taking the same length, let me take the a bigger length. So let me take this to be the line called as y equal to b, y equal to b. So we have the boundary y equal to b. So what happens over here is we have the closed curve C to be the boundary. So if I am going to mark this as my O and this point as my A, this point as my B and this point as my C. So which is my curve, closed curve C, which has been given in the problem, which I am going to circulate along, will be OA, AB, BC and CO. You have to keep in mind we will always have to traverse in anti-clockwise direction. Now let us mark the ordinates required for it. So this is O, x equal to 0, y equal to 0. Always the coordinates are marked as x comma y. What is the value taken by x? X takes the value 0. What is the value taken by y? Y takes the value 0. So the point O is 0 comma 0. Now coming to the point A, x takes the value A, y takes the value 0. So the point A is A comma 0. Now moving to the point B, x takes the value A and y takes the value B. So the point B is A comma B. Now coming to the point C, x takes the value 0, y takes the value B. So the point C is 0 comma B. So I have now fixed my points of references and what are going to be their coordinates. Now this will help me to integrate the region over here. Now come on, identify the statement what we know about by the Green's theorem in the plane. Integral over C p dx plus q dy equal to double integral over r dou q by dou x minus dou p by dou y dx dy. Now this integral along my curve C, what I am going to do is integral along the curve C. I am splitting it as 4 parts. Integral along the first, this is going to be my C which I am going to traverse. So first along my OA, next along my, this is going to be my AB, next along my BC and last along my CO. So when I add all the 4 integrals, that is equal to evaluating around the curve called as C. So now let us see how we can go about evaluating this integral. Now let us begin our integration with respect to the first line called as OA. Along the OA, what is the name of the line OA? Along the line OA, I have the name of the line as y equal to 0. If y equal to 0, what happens to its derivative? Dy will also turn out to be equal to 0. This has to be evaluated for the expression x square minus y square dx plus 2xy dy. Now along the curve OA, what will happen to this expression? I will substitute y equal to 0 and dy equal to 0 over here. So this dy will vanish, this y square will vanish. So my AO will now be acting only upon the quantity x square dx. Now what is the variable of integration? The variable of integration is x. So now let us fix the limit for my x, which is my limit for x. So now coming to my limit for x, my x begins with 0, it moves in this direction and my x ends with a. So my limit for my x is x varies between 0 to a. If I am going to integrate x square, it becomes x cube by 3 between the limit 0 to a, and hence I have the answer as a cube by 3. My first line is done. Now let us move to the second line. What is my second line? Along the line AB. What is the name of the line AB? The name of the line AB is x equal to a. If I have x equal to a, differentiating on both sides, I have dx to be equal to 0, where we will have to substitute all these quantities into the original equation. So when I substitute it in the original equation, dx equal to 0, so this will vanish, and what will be left out is only this part of here. Okay, so you will have integral over AB. This will give me 2 times of, what is x to be replaced over here? X will be replaced as a, and you will have a y with respect to dy. Now what is the limit? The limit is in the direction of y. So let me move and find the limit in the direction of y. Where does my y move now? my y moves from, so go on with the y coordinate, which is the y coordinate. This is my y coordinate. In the direction it moves from 0 and it moves till the point. It moves in this direction to reach the point called as b. So the integration will happen between y varying from 0 to b. So now this gives me 2a is a constant. Y on integration is y square divided by 2. When you apply the limit, 2 cancels off between 0 to b. The answer for it will be equal to a into b square. This is my value along the line AB. Now coming to the third line. What is my third line? Along the line y equal to b. So that is traveling in the direction of BC. In the direction of BC, what is the name of the line BC? Y equal to b. If I substitute y equal to b, what will happen to my dy? Differentiating on both sides, I have dy to be equal to 0. So what will happen? The second term vanishes, leaving you with just the first term. So what is going to be the first term? X square minus y square. What is y to be replaced with? B. So it is x square minus b square times dx. So now this has to be integrated with respect to which variable? In the x direction. So come on, let us check what is happening in the x direction. So what happens to my limit over here in the x direction? My x moves from the point x is equal to a and it moves over here to the point called as 0. So be careful, x moves from a to the point 0. So highlight it over here, integral x moving from a to 0. So usually don't take it in the sense that 0 will be lower, a will be upper. Since over here we are moving in the anti-clockwise direction, what happens? A comes first and then comes your 0. Okay, so be careful, very careful about the direction or the orientation. Where does your x move? X moves from a to 0. What you'll have to integrate is x square minus b square times your dx. So this will give me x cube divided by 3 minus b square times of my x between the limits 0 and a. When I apply the upper limit will become 0 minus lower limit will become a cube divided by 3 and minus of minus will become plus b square times of a. So I am done with the third curve. OA is over, AB is over, BC is over. What is going to be the fourth curve? The fourth curve is along the direction over here, CO. Name of the curve CO. What is the equation of the CO? CO is given by x equal to 0. When x equal to 0, what will happen to your dx? Dx will also be equal to 0. So what will happen to the quantity? Dx is present over here, so this will vanish. X is present over here, so this will vanish. So totally the value along the curve CO will be equal to 0. So now try to accumulate all the values which have been occurring for the integration over the C. So integration over the C, the first term is a cube by 3. Along AB, the value is going to be AB square. Along BC, it is going to be minus a cube by 3 and plus AB square, and the fourth value is going to be equal to 0. Now what is my C? C is the addition of all the four. So when I take the addition of all the four, what will happen to me is we add on top each, we'll have integral over C, integral over OA plus integral over AB plus integral over BC plus integral over CO. So when we have it, this will be equal to along OA. What was along OA? A cube by 3. So this is A cube divided by 3. Along AB, how much we have? Along AB, I have AB square. This is AB square. And now for it, BC, it is going to be minus a cube by 3 minus into minus plus ab square, and for the last part we have it to be equal to 0. So we have added all the four parts of my curve so that my closed curve C has been evaluated for. So this answer, or my left hand side of my Green's theorem, lands up to a cube and a cube cancels off, ab square makes it as 2ab square. So my left hand side of my Green's theorem gives me the value as 2ab square. So now moving on to your right hand side. What is going to be on the right hand side? We'll go back and see. So this is going to be my dou q by dou x minus dou p by dou y dx dy. So I need to extract my p and q from my equation and then differentiate them partially with respect to x and y. Now observe the relationship of the given term with that of the Green's theorem. What do we have in place of p? That is, along attached with the dx, we have p. Attached with p dx, we have p. So what is my p? My value of p is going to be equal to x square minus y square. Now, what is attached along with dy will be referred as q. So, which is my q from over here? Q is going to be equal to 2xy. So, now I have p, I have q. What does my right hand side require now? Dou q by dou x. So, what will be dou q by dou x? Differentiate q partially with respect to x. So, when we differentiate, the answer is going to be 2. Y is a constant, x on differentiation is 1. So now next let us move on to differentiate dou p with respect to dou y. With respect to py, the first term becomes 0 and the second term gives me minus 2y. So I have dou q by dou x minus of dou p by dou y. So when I subtract dou q by dou x from my dou p by dou y, what will I have? I will have 2y minus of minus 2y. So the total value will be equal to 4y. So now let us begin the estimation for our right hand side. So what we will have to do? A right hand side is double integral. How to fix the double integral? I need a limit for my x and I need a limit for my y. How to go about it? Which is my closed area? This is my region R. So in this region R, to fix my limits, let me draw a line parallel to my x-axis to fix my limits. So when I draw a line in a direction of my x-axis, this is going to be my x-axis. So where does my x vary from to? My x varies from 0 to x varies from a. So the limit for my x will be from 0 to a. So this fixes the limit for my x direction. Now in the direction of y, so where does your y vary? Y varies from the bottom to the top. So tell me, where is your lower point of y and where is your upper point of y? Y begins its journey with 0 and where does y end its journey? Ends its journey at b. So my double integration is happening between 0 to a and 0 to b. Come on, now we will substitute this for the required quantity. So my right hand side of my RHS of my Green's theorem says double integral over R dou Q divided by your value over here dou X minus dou P by dou Y dx dy minus dou P by dou Y. This is going to be dx dy. So what you have is double integral. The inside part we have evaluated it to be equal to 4y dx dy. What is for me first? X. So my x varies between 0 to a. What is coming next is my y. Y varies between 0 to b. So now this can be evaluated as with respect to x first. 4y is a constant. So dx on integration gives you x between the limits 0 to a. Still we have y varying from 0 to b, dy to be left out. So it is 4y times of a to be integrated between 0 to b dy. So when I integrate it with respect to y, 4a is a constant. Y on integration gives us y square divided by 2. Now apply the limit between 0 to b. So 2 can be cancelled off over here. So this gives me 2a upper limit minus the lower limit gives me b square minus 0. So what is going to be my right hand side? My right hand side is going to be evaluated as 2ab square. Now let us go and check what we had for your left hand side. It is 2ab square. So we notice that 2ab square is the same as 2ab square. That is your LHS is equal to RHS. So what we have verified? We have verified that the left hand side of your Green's theorem is the same as your right hand side of your Green's theorem. Hence, Green's theorem has been proved for this plane, which is a rectangular one, for this function x square minus y square dx plus 2xy dy. Thank you.